Welcome everyone. So this particular note section that we're going to discuss focuses on talking about this new type of motion that we started discussing a couple days ago. And we're going to kind of keep talking a little bit more about exactly what it means when I talk about things that are accelerated motion. All right? Now, just like we did before, whenever we start to talk about a new unit, we want to define some terms just to make it a little bit easier for us to understand what's going on. And so we have some new definitions, some new things we can look for. So I've already taken the liberty, if you notice, I've actually already filled out this entire table for you. But it's just kind of talking about some different quantities that we can measure or we might want to try and find when we start about things that are accelerated. Now you should notice most of these seem very familiar because we've already talked about them when we discussed constant velocity. So what we're discussing here is basically reminding ourselves the things we already know about and just adding a couple more about what might be important when we talk about accelerated motion. All right? So you notice we're starting at the top. We start with the idea of position. And remember, we've already defined position. Honestly, I'm not going to take too much time to kind of redefine all these things because they're already written down. But the position is basically where I am with respect to an origin. All right? Now remember, your position could be positive or negative because I could be in front of or behind the origin, depending on how we're defining it. All right? But the symbol is a little x. Units of measurement are going to be meters. Next is going to be time. And remember, position and time are fundamentally two of the easiest things that we can measure that tell us a ton of stuff about an object. Now remember, time is just how long something takes. Symbol is a little t. Units are going to be in seconds. Now, next is something referred to as displacement. Now, we talked about displacement a little bit. We talked about the idea of distance as well. We're going to focus specifically on displacement right now. Now, displacement might seem very strange at first because it's kind of a new word, but honestly, all displacement is just measuring the change in position, or it's literally measuring how much is my end position change from my starting position. Now, displacement can also be positive or negative because I could end up in front of where I started or behind where I started. All right, remember, again, positive or negative in physics class just means I'm going in the positive direction or I'm in the negative direction. It doesn't mean bigger or smaller. Symbol is going to be this little triangle, which is referred to as delta, because in math language, delta means change. So it's delta x. Units, again, are only measured in meters. After that is velocity. And again, velocity is something we've talked about a bunch already within this constant velocity unit, so we're just kind of refreshing our mind on what it is. But velocity is speed with direction. All right, remember, velocity is literally how fast we are going and the direction we are going in. All right, and again, that can be positive or negative as well because it could either be, I could be going in the positive direction or the negative direction depending on how I am moving. Symbol, little v. Units are going to be meters per second because remember, velocity is basically measuring how many meters you travel every second. Now, for the two new definitions that we kind of added here, the first is direction. And direction is about as simple as it sounds. We're going to define it as just saying is which way I am going. And it is going to, again, it can be either positive or negative. Direction actually can be several different things depending on how you kind of show direction. It could be positive or negative. It could be like the things on a compass where you're talking about north, south, east, west. It could be in degrees, depending on kind of how you're doing it. It's really however you decide to dictate what direction looks like. In our class, it's usually just going to be positive or negative. Now, for the sixth and final one, the most important one in this brand new unit is the new quantity of motion we're going to measure, which is acceleration. Right? Now, acceleration pops up a lot in the English language. In physics, we use it in a very specific way. And acceleration basically measures how much I speed up or slow down in some time frame or some amount of time. It's basically measuring how much velocity did I gain or lose in a second. All right. Now, the symbol for acceleration is a little a, and it's units. The units should look a little bit weird. You will normally see me write them as meters per second squared. So it would be a meter. It would be an m over an s squared. But what that really means is meters per second every second. So what acceleration is trying to tell us is it's telling us how many meters per second, how much velocity is going to change every second. All right, so it's basically a measurement of telling me how much I'm going to speed up or slow down in 1 second is kind of the main focus of acceleration here. And we're going to keep working through this for the next couple of days to kind of discuss a little more about what acceleration is and how exactly it matters. All right. Well, the best way in order to see this is honestly to practice a little bit. So you'll notice there are 8 graphs right here. So these are 8 different position time graphs. What we're going to do is I've actually given you 5 different scenarios right here. And what I would like you to do is I would like you to kind of go piece by piece through these and try and figure out which graph matches with which scenario. All right. Now we're going to go 2 at a time. So we're going to start with just the first 2. So if you could pause the video, Take as much time as you need. And then once you kind of give an idea, come back and we'll talk about for scenario 1 and scenario 2. All right, so scenario 1, a block is dropped from rest with a height of 1 meter above the floor. Take the origin to be at the level of the floor, which basically means the height is at the floor height is 0. And then the second scenario, a rocket slide is ignited and the sled starts moving forward on flat ground. Now, one thing I'll say about the first scenario before you go to this is in order to kind of help you figure out what that motion looks like, I would highly recommend just grabbing something next to you that you can drop and dropping it and kind of observing how it moves. All right? So with that being said, if you could please pause the video, take as much time as you need to. When you think you've got an idea, come back and we'll talk about it. Fantastic. So I hope you had a chance to kind of play around with the first and second ideas and the first and second graphs. So let's talk a little bit about what it looks like when I drop something. So if I say a block is dropped from rest, and if you had a chance to do that, you probably noticed that the block started to speed up as it was falling. All right, because when I let go of it, it didn't have any velocity, but it clearly did by the time all was said and done. So it is speeding up. Now, right away, when we kind of think about this, it lets us kind of eliminate some graphs just based off of that alone. So let's take a look at these graphs. Of all the graphs we see here, speeding up means that it's not going to be a linear graph when we're talking about position versus time graph. So already we can toss a couple of these. A, B, and F can go away because they're all linear graphs, so they don't help us at all. G also can be thrown away because G is also talking about some sort of constant velocity because it's linear. So again, toss that one out. So we're left with C, D, E, and H. Now, the next piece we want to look for is the idea that it is speeding up. If it's speeding up, it means that the graph has to be getting steeper. All right. Now, it doesn't really eliminate too many of them because it looks like C, D, and E are all getting steeper. But H, on the other hand, seems to be showing something that's slightly different than all the other ones because it seems to be getting less steep and then steeper. So H, I think, seems to be more complicated than we need. So H can be thrown away as well. So we're left with C, D, and E. Now, the next piece we want to ask ourselves is which way is this going? Because it might help us figure out which graph we need. If I drop it, more than likely based off of kind of how we ever think about things going up and down, if it is falling down, we can assume that means it's moving in the negative direction. This is actually our first real example of something that is moving in a kind of vertical plane, but it still follows the exact same rule. So in this case, it's falling down. So we need a graph that is showing this object is moving in the negative direction. So between C, D, and E, that throws C out the window because unfortunately C is going in the positive direction. So we're left with D and E, which takes us back to the final piece of information in this. It says that we drop it from a height of 1 meter and then it basically starts going towards the floor. Now we define the floor as the origin, so the floor is a height of 0, which means that basically this object is falling towards 0 based off of this. Well, looking at the only two graphs left, D and E, D is the only one that shows an object that starts at a height above 0 and then starts basically falling towards it, speeding up. So the answer for 1 is going to be D. Right? And the next one, this might be a little bit simpler. A rocket sled is ignited and the sled starts moving forward on flat ground. Now, we haven't talked too much about kind of what is going on here and what physical situations. When we get to our next unit, we will. But I'm willing to bet that most of you kind of decided that a rocket sled will start to speed up once you light it, which means we need just something a graph that is speeding up. And again, in this case, we can probably assume it's moving forward, so it's moving in a positive direction. So we need a graph that is speeding up in the positive direction. And of all 8 graphs that are up here, the only one that works is C. All right, so again, all we're doing right now is we're just taking stuff that we've already discussed, taking these ideas that we can see from things that are speeding up to things we've seen in the lab, and we're just applying them to these new graphs. Now, 3 and 4, same deal. I want you to go through. I want you to kind of read the scenario, think about which graphs match it. Pause the video once you think, kind of work through it, and once you're ready, unpause it, and we'll go from there. All right, so hopefully you had a chance to work through 3 and 4 as well. Now, 3 and 4 are slightly different, or a little bit more interesting than the rest, because 3 and 4 both talk about something that is changing direction, which means that we can already kind of eliminate most of the graphs for 3 and 4 because we need something that demonstrates a changing direction. And the only graphs that do that are G and H, because G and H are showing something that might be, in both cases, they start going positively and then they end up going negatively. All right. Now, for scenario 3, it says a ball is thrown straight up into the air. When I do that, and if you could, grab something, toss it up in the air and let it fall back to your hand, you'll notice that it doesn't seem to go at a consistent velocity. Instead, what you'll probably notice that as it's starting to go up in the air, it's eventually slowing down until it reaches some high point, and then it starts to fall back to your hand and starts speeding up. So for scenario 3, we need an object that is changing direction, but is also speeding up or showing some sort of accelerated motion. In this case, you just slow down, then speed up. The other graph that works for that is H, because H is showing in the beginning something that is moving in the positive direction, so it's going up, but it is also getting less and less steep, which means it is slowing down. And of course, the second piece, it's now starting to speed back up because it's getting steeper and steeper, and it's moving in the negative direction. So that's the only one that works. Now, for number 4, this one, it says a ball rolls along a horizontal surface without changing speed. So right away, you're looking for a graph that is showing something that is going at a constant velocity, and then it hits the wall, and it basically rebounds and goes the other way at the exact same speed, but in the opposite direction. Well, we already discussed there's only 2 graphs that show change of direction, and since it's not H, because H is not showing constant velocity, it has to be G. Fantastic. Now, for number 5, I'm going to tell you, if you look at the 8 graphs, the 5th scenario actually does not match any of them. It's kind of a trick question. I don't do that very often, but every now and then I want to throw in there, see if we're paying attention. In fact, there is no graph that shows something where an object is moving forward in the positive direction, but slowing down. So what I want you to do is that just somewhere, piece of paper, whatever you got, or just kind of in your head, take like 90 seconds to think about what should it look like if I wanted to draw a graph, a position graph specifically, that showed an object that was slowing down, but in the positive direction. All right, so hopefully you had a chance to kind of think through that. If you did that, you'll actually notice that what you should have drawn is something that looks like just the first half of graph H. So if it's going in the positive direction, that means I need to have the position graph moving in the positive direction. But because it is slowing down to a stop, it needs to be getting less and less steep. So you should be drawing a graph that basically looks kind of like a curve that starts really, really steep, but it's getting less, and it's getting flatter and flatter and flatter until it basically gets perfectly horizontal, right? And again, our main goal here is we're just trying to show that we can take these graphs and we can take these real world situations and we can relate the two to see that these graphs don't just mean something strange going forward. All right? Now, for the last piece of these notes, you're fantastic. Keep it up. We're going to look at another position time graph. And again, we're going to break it into little sections. And what I want you to do, if you don't mind, is I just want you to pause this video because I think at this point we know pretty much what we're doing. I want you to look at the position time graph, and I want you to answer the 3 questions, please. So pause the video at this point. Take as much time as you need to. And once you're ready, unpause it, and we'll talk about the last couple of answers for this. Fantastic. So I hope you had a chance to kind of go through and answer those 3 questions. So let's talk about it a little bit. So I already kind of pointed out that there are 4 sections of motion in this graph. And basically what's nice is every single square seems to basically relate to one of the sections. Now, the first question I asked is which sections appear to experience acceleration, some sort of speeding up or slowing down? Well, remember, when we're talking about acceleration, it means on a position time graph that the graph is curved. And of the 4 sections, the only 2 that are curved are the first section and the third section. So it's going to be section 1 and section 3. Now, section 1, because it's getting steeper, is speeding up. Section 3, because it's getting less steep, is getting flatter, slowing down. All right. Now, that means the other 2 sections are probably going to be the ones that experience constant velocity, which makes sense because these are both, looks like they're nice and linear, which means they are not changing at all. So it's going to be section 2 and section 4. Even though some people ask, if it's not moving, is it going at constant velocity? And it is. It's a constant velocity of 0. So even though it kind of seems a little strange, we're saying that it's still moving at constant velocity. All right. And then for the last piece, it says describe the motion of the starfish in words. You want to specify items such as constant velocity, the direction you're going in, if you're speeding up or slowing down, and where you are starting. So how I would describe this, and I'm not going to type it down, I'm just going to kind of say it, and then you can kind of phrase it into your own words, is I would start by saying this object starts at the origin, or excuse me, the starfish starts at the origin and begins to speed up in the positive direction. Right there, that's the first section. Then the starfish continues traveling at a positive constant velocity. Boom, second section done. The starfish then starts to slow down, still moving in the positive direction. Boom, third section. And finally, the starfish stops. And we got all 4 sections done. All right. So we're just once again kind of focusing on this idea that we can take these graphs and we can relate them back to real world situations. And while even then, how we're describing it still seems kind of physicsy, we could very easily connect this, use some context and connect this to a real situation. Maybe the starfish sees some food, so it's kind of heading over to the food, gets close to it, starts to slow down, reaches the food, so it's going to stop while it's eating. All right. So just what we want to kind of focus on here is the idea that we can take these graphs, we can take what we're discussing with accelerated motion, constant velocity, and we can relate it back to real world situations. All right. So with that being said, y'all, if you have any questions, please do not hesitate to come to office hours. Otherwise, have a great rest of the day.